In this video, we're going to talk about the normal curve. So the normal curve has a couple of different names. Most notably, the name that I'm gonna point out is what's called the bell-shaped curve. So AKA the bell-shaped curve. And that implies that it kind of shaped like a bell. All right, so let's talk about the bell-shaped curve and the normal curve. Okay, so first thing I want to point out with the normal curve is that the mean is actually at the center of the curve. So here is where the mean would be, either mu or x bar, whichever one we're referring to. And that is kind of just discussing what the data is. So with the bell-shaped curve, just to kind of get an understanding of it, it comes from the idea that if we were to draw a smooth curve on a histogram, this is what it would look like. So I'm going to just draw over here, like if we had, like, let's say this is our histogram. You could kind of tell that it somewhat has a bell shape to it. Okay, so some notable things then about the bell-shaped curve is that it is symmetrical. The idea is where the mean is supposed to split the curve in half. And it is supposed to be kind of like a mirror image on either side, even though I can't quite draw it that way. Okay, so even though it's not a perfect mirror image, it's supposed to be a mirror image on either side. Some famous examples of the bell-shaped curve are IQs. So IQ falls into the pattern of the bell-shaped curve, and I'm talking about, human IQs. So the idea is that most people are going to fall towards the middle where the average is. And then there are going to be a few people who fall far above average and a few people who are going to fall far below average. And IQ follows the bell-shaped curve, okay, or the normal curve. Okay, now there are some properties of the normal curve that we want to talk about and that are extremely useful. First of all, because the bell-shaped curve, the mean ends up being in the middle, the median also ends up being in the middle. And it kind of makes sense because you could kind of see that since it's symmetrical, it's going to fall on either side of the data there. Okay, so the mean is in the middle, and so is the median, and actually so is the mode. And that's because the majority of the data is grouped up in the middle. And if you're talking about kind of thinking about this from a histogram, that would be where the tallest rectangle is, implying that that's where the most data is, implying that that is the mode. Okay. Second, I already said this, but I want to write it. It's symmetrical. And in other words, 50% of the data lies below the mean. So over here is 50% of the data, and over here is the other 50% of the data. It splits it in half. Okay. Number 3. It represents probability. So we're actually going to use the bell-shaped curve to talk about probability. And that's really why we're introducing it at this point. I mean, we've had a whole long discussion about probability prior to this, and now we're going to use probability to help us analyze data. And that's what the normal curve is going to do for us. Okay, now before I state property number 4, I want to mention a really cool feature about the normal curve, and that is we can display standard deviation on the normal curve. So on the normal curve, standard deviation, so let's say this is 1 standard deviation away from the mean. Then this would be another standard deviation away from the mean, and another standard deviation away from the mean. In fact, with standard deviation on the normal curve, it is common to show or display 3 standard deviations above and below the mean. So each standard deviation takes us a little further away from the mean. And when we're looking at data that's farther away from the mean, that means it's more than one standard deviation away from the mean. What this sets us up for is something called the empirical rule. And that is our fourth property, the empirical rule. All right, I'm going to zoom out here just so I have a little bit of room to write. So the empirical rule works like this. One standard deviation away from the mean. And I'm going to abbreviate standard deviation as STND period DEV period. Okay, just because of space, I'm trying to save myself some space. So one standard deviation away from the mean represents 68% of the data. Approximately. It is approximate. So what that means is if I come over here to my normal curve, is that if I'm looking from here to here, this is about 68% of the data. More than half of the data, 2/3 of the data is within one standard deviation of the mean when you have data that looks like the normal curve. Okay, 2 standard deviations is 95% of the data. So let me go another standard deviation here. I'm going to switch to a different color. All right, green. Thank you. Oop, okay. Okay, so one more standard deviation away from the mean. Oh, it's lagging for a second, of course. All right, so now, sorry, I apologize that that took a little longer than I would have liked. This is 95% of the data. I mean, that's incredible when you think about it. 95% of the data is within 2 standard deviations of the mean. All right, and then 3 standard deviations is 99.7%. All right, so here we'll use the red one for the ladder, or for the outside one here. Actually, I'll draw it down below. It's a little bit easier. 99.7% of the 3 standard deviations of the mean. So what that tells us then is that when we look at these like little tails here at the end, there's possibly data there, but it's not a lot of data. It's only 0.3% of the data. And it kind of leaves the idea that those are potentially outlier data that, could exist in the world, but is probably not very likely to be there. All right. So kind of using all of this, and in particular, the empirical rule, I want to look at an example to kind of have some solid numbers for us to look at. So here. Okay, so suppose that standard amount of time to use a computer each day. So use a computer. Let's say it has a mean of 2 hours with a standard deviation of half an hour. All right. I want to make a note really quick. The book likes to use this notation to indicate shortcut way of writing this. So they would use, n of 2, 0.5 to represent a normal distribution with a mean of 2 and a standard deviation of 0.5. So just so we're clear, that's what that notation means. They also use X and then this little tilde symbol to indicate that the data we're talking about, because X is referring to our data, is normally distributed with a mean of 2 and a standard deviation of 0.5. Okay, so it's kind of a shortcut way of writing this information out. So I want to look at the normal curve for this. I want to kind of draw it out using this mean, this standard deviation. And then I would like to explore what the empirical rule looks like for this particular problem. I am going to switch to my black pen, which is a bit annoying, but oh well, we will do that. Okay, so I'm going to draw myself a nice normal curve as best I can. It's not going to be perfect, but I'll do my best. There we go. Okay, so for this problem, the mean is 2 hours, and that'll be here in the center. I won't put hours, I'll just put 2. And then I want to draw 3 standard deviations above and below the mean. So above the mean, since standard deviation is half an hour, this would be 2.5, and then add another half hour would be 3, and then 3.5. Then below the mean, meaning we'll be subtracting the standard deviation now. This will be 1.5, 1, and 0.5. Okay, so here's the middle. That's the mean. Okay, so according to the empirical rule, here's what we got. Between 1.5, so that's 1 standard deviation below the mean, and 2.5, which is 1 standard deviation above the mean, 1.5 to 2.5 hours, 68% of households use the computer this long. Okay, that's a bad sentence. Bad sentence. I was kind of trying to show you the range and the percent, but it's a terrible sentence. Let's do a better sentence for when we're talking about 2 standard deviations. Okay, so with 2 standard deviations, now we're looking at 1 to 3, and the percentage is now 95%. So we would say about 95% of households. Wow, that's not how you spell households. Households use the computer between 1 to 3 hours every day or per day. Much better sentence. There we go. Whew. All right. Take a second then. Write what it would be for 3 standard deviations. Okay. Maybe pause the video, write it yourself. Just verify that you'll write it the same way. Okay. All right. So about 99.7% of households use the computer half hour to 3.5 hours every day. All right, there we go. Of course, you could say per day. You can change the wording a smidge and still say the same idea. Now, here's what's kind of cool about the empirical rule. Because we know that this is 68%, this middle, right? These 2 here are 68%. That means I could figure out how much data this is representing on this curve, okay? Because if from here to here, from the whole thing is 68%, and we know this is symmetrical and the mean cuts it in half, that would mean if I divided 68% by 2, this would represent 34% of the data. And so would this. So both of these individually represent 34% of the data. So that means if I were to say, what percent of households use the computer between 2 to 2.5 hours every day, you would say 34%. Because between 2 and 2.5 hours, that's just that block, and that's 34%. So here, let me write that down. 34% of households use the computer 2 to 2.5 hours daily. I'm going to go ahead and put little bullet marks for each statement I'm making here. And what's neat then is that we can find the percentages now that we kind of see that based on different values. So like, let's say I wanted to figure out what percent is between, let's do 1 and 3.5. I'm going to write this question down first. What percent is between 1 to 3.5 hours? Okay, so let me come back up here. So 1 to 3.5. That means we're looking at, oops, here's 1, which is 2 standard deviations below, and 3.5, which is 3 standard deviations above. So here's what I'd like to figure out then. I want to figure out what percents each of these little blocks represent. Here, I'm going to switch to green just so I have a contrasting color. I'd like to figure out, oops, what percent that one is. And this one, they'll both be equal. And then I'd like to figure out, let me get my blue here, what percent this one is, and this one. Again, those will be equal. And then what I can do is if I want to go from 1 to 3.5, I'll add those all together. Okay, that's what I'll do. Now, I'm going to show you that you don't have to quite do it this way, but we are going to go ahead and figure these out really quick. So here we go. So for 2 standard deviations, which is from 1 to 3, that's supposed to be 95% of the data. Okay, so if I grab my calculator and take 95 and divide it by 2, that's going to give me 47.5. I'm just going to write this down on the side. Okay, so what that means is from 2 to 3, this is 47.5. And from 1 to 2, this is 47.5. But 34% is already accounted for in the little red area here. So if I want to figure out how much is left over, I would need to take 47.5 and subtract 34. So 47.5 minus 34 gives me 13.5. So that's taking 47.5 minus 34 equals 13.5%. And notice if I take 34 and add 13.5, I get 47.5 from that. Okay, so that means this is also 13.5%. All right, now let's do the blue one. I'm going to go ahead and erase my work underneath here to do that. So the blue one then, 3 standard deviations from here to here is 99.7%, which I'm going to go ahead and cut in half. That's a decimal there. So 99.7 divided by 2 on my calculator gives me 49.85. So from here to here is 49.85%. And this is 49.85% as well, from the mean out to the 3rd standard deviation. All right. Now, in order to figure out the little blue area, I need to subtract the red and the green. All right. So if I take 49, I'm going to write this down, 49.85, and subtract 34 and also 13.5. So 49.85. Sorry, that's like really sloppy the way it's written. Let me try to clean it up so it's a little bit more readable. 49.85. Okay. Get my calculator. 49.85 minus 34 minus 13.5 gives me 2.35. So this little blue area represents 2.35%. And this blue area also represents 2.35%. So notice the percentages are going down the further away we get from the mean. That makes sense because data is less likely to be that far away from the mean. All right, so now back to my original question. I was interested in figuring out what data lies between, what percent is between 1 and 3. So I'm going to add, 1 and 3.5. Sorry, 1 and 3.5. So I'm going to add 13.5, 34, 34, 13.5, and 2.35 to figure that out. So come down here and do that. So 13.5, 34, 34, 13.5, and 2.35. So let me add those together. And I get 97.35%. Okay, now write that down. If you need to pause the video before I continue, that's fine. But I want to say there's other ways to figure that out. There's other ways to do that. Now that I kind of see these percent breakdowns, I didn't have to add all of those numbers together to figure it out. I could have taken the larger standard deviation amount. In other words, I could have gone from 0.5 to 3.5, which is 99.7, and subtracted one of the 2.5s because this one ends up not being part of the numbers we're looking at. All right, that's one way to do it. I could have taken the fact that this is 95% of the data right here and added 2.5 to it. And that would have also represented the same area. So you didn't have to use these individualized areas to do it. Now, here's what's kind of cool. Like the empirical rule, these percentages aren't really going to change. So you can use these percents over and over again on normal curves to kind of figure out these types of questions. All right. But there we go. That is the normal curve.